Welcome to the deep dive. We're here to plunge into some really fascinating corners of knowledge, hoping to pull out insights that, leave you feeling truly well-informed. And space. There's just something about it, isn't there? The scale, it just kind of bends your mind. All those wonders out there. Today, we're doing more than just looking at a pretty picture from space. We're taking a real deep dive into one specific thing, the Abell 209 galaxy cluster. Our mission, if you will, is to unpack how just one image, a stunning one from Hubble, but still one image, can tell us so much about the invisible universe. We're talking dark matter, even the fabric of space-time itself.
Yeah, Abell 209, it's an incredible target. The name itself sounds pretty epic, doesn't it?
It does.
And it really lives up to it. I mean, we're looking at this colossal structure, something like 2.8 billion light years away, way out there in the constellation Cetus. And yes, it is visually spectacular, but it's so much more than just, a nice image. Abell 209 is, it's like a powerful tool, a cosmic laboratory, really. It helps us test fundamental physics, the rules governing everything. It's quite literally a window into the unseen.
Okay, so let's start with what we can actually see. When you first look at that Hubble image of Abell 209, wasn't it Narcissa's picture of the week at some point?
It was, yeah. Deservedly so.
The visual impact is just, wow, hundreds of galaxies packed in there. You've got that huge central galaxy right in the middle, kind of dominating everything. And then surrounding it, dozens of these glowing bluish spiral galaxies. You can even make out the arms and bright cores in some of them. And even further out, you see these fainter specks, more distant galaxies peeking through. It really shows the variety. But that big central galaxy, it's not just pretty, is it? Does its size tell us something important?
Oh, absolutely. It's much more than just an anchor for the view. The really crucial point is its intense gravity. That massive galaxy plus, the combined gravity of all the galaxies in the cluster, that's what powers this amazing phenomenon called gravitational lensing.
Ah, lensing.
Yeah, exactly. The cluster's gravity acts like a giant cosmic magnifying glass. It literally bends the light from objects behind it as that light travels towards us.
Okay, so that's the luminous side, the bright galaxies we see. But the universe is pretty good at hiding things, right?
Mm-hmm.
What else is filling up all that space between the galaxies in a cluster like Abell 209? It can't just be empty void.
You're absolutely right. The visible galaxies, as stunning as they are, they're really only part of the picture. That space between them, what we call the intra-cluster medium, it's definitely not empty. It's full of this incredibly hot gas.
Hot gas. How hot are we talking?
We're talking tens of millions of degrees.
Right.
Searing hot. Now, this gas is very, very diffuse, super spread out, but there's just an enormous amount of it. But here's the catch. Because it's so incredibly hot, it doesn't glow in visible light like stars do. Mm-hmm. Instead, it radiates mostly in X-rays. Mm. So to optical telescopes like Hubble, it's basically invisible, a ghost in the machine almost.
Okay.
So to really understand the total baryonic mass, that's all the normal matter, atoms, the stuff we're made of, you absolutely need other kinds of telescopes. X-ray telescopes are key here.
Right, and this is where it starts getting really wild, because you mentioned normal matter, the galaxies, the hot gas we can see or infer. But the thing about Abell 209 that just blows my mind is this fact. You add all that stuff up, and it's only about, 20% of the cluster's total mass?
That's right, roughly 20%.
So 80% is just missing, or, invisible. Which brings us to dark matter. This completely mysterious stuff we only know exists because we see its gravity pulling things around. It makes up the other 80%. But the big question is always, if you can't see it, how in the world do astronomers actually, map it out? Where is it?
And that is precisely where gravitational lensing becomes absolutely essential. It's our primary tool. Think about space-time, the fabric of the universe. Immense mass, like this galaxy cluster, warps it, like putting a heavy bowling ball on a stretched rubber sheet.
Okay, yeah, the classic analogy.
Right. So light from galaxies far behind the cluster has to travel through this warped, curved space to reach us.
And it gets bent.
It's bent, distorted, stretched, sometimes even magnified or multiplied into multiple images or arcs. By carefully, meticulously analyzing how much those background galaxies are distorted, how stretched or smeared they look, researchers can work backwards. They can literally construct detailed maps showing where the gravity is strongest and therefore where the unseen mass, the dark matter, must be concentrated.
Wow. So you're mapping the invisible by seeing how it bends light from things even further away.
Exactly. And what's really exciting now is that these maps are getting so detailed, they're not just telling us where it is, but maybe hinting at its properties, its sort of texture. It pushes us closer to figuring out what this stuff actually is. It's genuinely one of the biggest puzzles in physics. And lensing, is our best detective on the case.
That just sounds like an incredibly powerful technique, almost like a cheat code for cosmology. So this lensing effect, it's not just for hunting dark matter then. You called it a cosmic Swiss Army knife earlier. What other jobs does it do?
Oh, it's incredibly versatile.
Hmm.
First, like we sort of touched on, it acts as a natural telescope by magnifying and brightening those really distant background galaxies, things that would otherwise be way too faint for even Hubble to see clearly.
Right.
It lets us effectively peer deeper into the early universe, see some of the first galaxies forming.
Amazing. And the second use?
Secondly, it acts as a surprisingly precise distance marker.
Yeah.
Measuring exactly how much the light is bent by the cluster's gravity gives us another way to estimate cosmic distances. Getting accurate distances on that scale is notoriously tricky.
I bet.
And if you can refine distance measurements, you can get a better handle on the Hubble constant, that crucial value telling us how fast the universe is expanding. There's still some tension, some disagreement between different methods measuring the Hubble constant, so every new independent measurement, like those derived from lensing in clusters like Abell 209, helps us zero in on the true value.
That's really remarkable. Just observing these incredibly distant things like Abell 209 directly affects how we understand the basic rules of the universe. It's not just about cataloging what's out there. It's actually testing the foundations of physics itself.
Precisely. Clusters like Abell 209 are fantastic laboratories for testing Einstein's theory of general relativity, but on truly enormous scales, much bigger than anything we can test here on Earth.
How so? What are you looking for?
Well, what's so compelling is that general relativity makes very specific predictions about how much light should bend given a certain amount of mass. If we map the visible matter, map the dark matter using lensing, and then observe lensing effects that don't quite match what the theory predicts.
Like if the light bends more or less than expected.
Exactly. Any deviation, even a subtle one, could be a huge deal. It might hint at new physics beyond Einstein, or maybe even suggest that our theory of gravity needs modification on these vast cosmic scales. It could point towards something completely unexpected about gravity or dark matter interactions.
So these observations are constantly pushing the boundaries, checking if our current theories hold up under extreme conditions.
That's the heart of the scientific method, isn't it? Always probing, always questioning, using these incredible cosmic structures as our testing grounds. Abell 209 is a perfect example.
And throughout this whole deep dive, we keep coming back to Hubble. We mentioned its iconic status at the start, and it really is amazing how decades on, it's still delivering this kind of groundbreaking science.
It absolutely is. Hubble's legacy is just immense. It remains a cornerstone of observational cosmology, no question. I mean, think about its contributions, revealing the structure of galaxy clusters like Abell 209 in such detail, pioneering the techniques to map dark matter through lensing, helping nail down cosmic distances, observing supernovae to probe cosmic acceleration. The list goes on.
Yeah.
Its images and data continue to inspire and inform, constantly driving new research and honestly just sparking curiosity in everyone who sees them. It's a testament to human ingenuity.
It really is incredible when you step back and think about it. The sheer depth of knowledge we've unpacked just by looking closely at this one cluster, Abell 209, from those dazzling galaxies we can see to the indivisible inferno of hot gas, and then diving into that huge mystery of dark matter, all teased out by watching how light bends across billions of light years.
And it really highlights the idea that knowledge isn't just about collecting facts, right? It's about understanding and applying them. Being able to look that far back in time, measure something as elusive as dark matter's distribution, it directly shapes our understanding of the universe's fundamental laws and ultimately our own place within it all.
So as we wrap up this deep dive, maybe something to think about is what comes next? What new mysteries will future observations of clusters like Abell 209, maybe with even more powerful telescopes, unlock? And, how might our current picture of gravity, of the whole universe, change just by keep watching how space-time gets warped out there? When you think about that 80% of the universe we apparently can't see, what stands out to you as the biggest question we still need to answer?